A vector is something that has both magnitude and direction. Magnitude and direction. So let's think of an example of what wouldn't and what would be a vector. So if someone tells you that something is moving at 5 miles per hour, this information by itself is not a vector quantity. It's only specifying a magnitude. We don't know what direction this thing is moving 5 miles per hour in. So this right over here, which is often referred to as a speed, this is a speed, is not a vector quantity just by itself. This is considered to be a scalar quantity. If we want it to be a vector, we would also have to specify the direction. So for example, someone might say it's moving 5 miles per hour east. So let's say it's moving 5 miles per hour due east. So now this combined 5 miles per hour due east, this is a vector quantity, and now we wouldn't call it speed anymore. We would call it velocity. So velocity is a vector. We're specifying the magnitude 5 miles per hour and the direction east. But how can we actually visualize this? So let's say we're operating in 2 dimensions. And what's neat about linear algebra is obviously a lot of what applies in 2 dimensions will extend to 3, and then even 4, 5, 6, as many dimensions as we want. Our brains have trouble visualizing beyond 3, but what's neat is we can mathematically deal with beyond 3 using linear algebra, and we'll see that in future videos. But let's just go back to our straight traditional 2-dimensional vector right over here. So one way we could represent it as an arrow that is 5 units long. We'll assume that each of our units, our unit here is miles per hour, and that's pointed to the right, where we'll say the right is east. So for example, I could start an arrow right over here, and I could make its length 5. The length of the arrow specifies the magnitude. So 1, 2, 3, 4, 5. And then the direction that the arrow is pointed in specifies its direction. So this right over here could represent visually this vector. If we say that the horizontal axis is, say, east, or the positive horizontal direction is moving in the east, this would be west, that would be north, and then that would be south. Now, what's interesting about vectors is that we only care about the magnitude and the direction. We don't necessarily care where we start, where we place it when we think about it visually like this. So for example, this would be the exact same vector, or would be equivalent vector to this. This vector has the same length, so it has the same magnitude, has a length of 5, and its direction is also due east. So these 2 vectors are equivalent. Now, one thing that you might say is, well, that's fair enough, but how do we represent it with a little bit more mathematical notation so we don't have to draw it every time and we can start performing operations on it? Well, the typical way, one, if you want a variable to represent a vector, is usually a lowercase letter. If you're publishing a book, you can bold it, but when you're doing it in your notebook, you would typically put a little arrow on top of it. And there's several ways that you could do it. You could literally say, hey, 5 miles per hour east, but that doesn't feel like you can really operate on that easily. The typical way is to specify, if you're in 2 dimensions, to specify 2 numbers that tell you how much is this vector moving in each of these dimensions. So for example, this one only moves in the horizontal dimension. And so we'll put our horizontal dimension first. So you might call this vector 5, 0. It's moving 5, positive 5, in the horizontal direction, and it's not moving at all in the vertical direction. And the notation might change. You might also see notation, and actually in a linear algebra context, it's more typical to write it as a column vector like this, 5, 0. This, once again, the first coordinate represents how much we're moving in the horizontal direction, and the second coordinate represents how much are we moving in the vertical direction. Now, this one isn't that interesting. You could have other vectors. You could have a vector that looks like this. It's moving, let's say it's moving 3 in the horizontal direction and positive 4. So 1, 2, 3, 4 in the vertical direction. So let me see. It might look something like this. So this could be another vector right over here. Maybe we call this vector vector A. And once again, I want to specify that it is a vector. And you see here that if you were to break it down in the horizontal direction, it is moving 3, or it's shifting 3 in the horizontal direction, and it's shifting 4, positive 4 in the vertical direction. So, and we get that by literally thinking about how much we're moving up and how much we're moving to the right when we start at the end of the arrow and go to the front of it. So this vector might be specified as 3, 3, 4, 3, 4. And you could use a Pythagorean theorem to figure out the actual length of this vector. And you'll see, because this is a 3, 4, 5 triangle, that this actually has a magnitude of 5. And as we study more and more linear algebra, we're going to start extending these to multiple dimensions. Obviously, we can visualize up to 3 dimensions. In 4 dimensions, it becomes more abstract. And that's why this type of a notation is useful, because it's very hard to draw a 4, 5, or 20-dimensional arrow like this.